Good afternoon, everyone. Welcome to the Rural Water webinar series and session on water quality sampling and analysis. My name is Dave Wetherell. Now, this webinar will provide a review of water sampling methods and subsequent analysis for water operators, field sample technicians, and others. Your presenter today will be talking about equipment used, calibrating, cleaning, and maintaining instruments, common field measurements, sample collection and testing, and evaluating results. Just some logistics. There will be questions taken via Q&A during the session. Q&A box is available to the right of your screen. We'll take questions via this box, and then at the end of the presentation, we'll answer as many questions as we can given the time allotted for the presentation. For any questions that we don't have time for, we'll follow up with emails to the appropriate individuals. We also welcome any comments, ideas, suggestions, or anything else you may have regarding the presentation. This presentation will be recorded and available for review after the session has been completed. So let's get started. Our presenter today is Ernie Rector, Market Manager at the LaMotte Company in Chestertown, Maryland. Ernie began working as the Market Manager handling the industrial water and wastewater sections for the LaMotte Company in 2010. His previous experience was as a water operator and laboratory technician at a public drinking water utility for 25 years. He graduated from the Delaware Technical and Community College with an AAS in chemistry technology. Ernie, thanks for joining us.
Well, thank you for that introduction, Dave. And I do want to start by letting everyone know that I am battling a bit of a cold right now, so I hope you will all bear with me if I sneeze or cough during the presentation. Again, this is a webinar dealing with water quality sampling methods, just standard procedures for field technicians, the kind of things you're going to do out in the field. A few of the things we're going to go over during this are general equipment that you're going to have to use out in the field, calibrations for that equipment, what kind of things you're testing for, how best to collect those samples that you're going to be testing, and then once you've collected the sample, how to go about the actual testing process, the best way to record your results so that you're conveying the information that you need back to your central site or to the commercial laboratory later. And then we'll go over briefly some of the things that are usually not sampled for, but not tested out in the field. These are things that are usually analyzed back at a central laboratory. There are a few types of sampling procedures, a few types of the testing that are done. Usually the ones you're going to run into are a colorimetric type of testing, which basically is a reagent type of system where you add a reagent to the sample and it turns color, and then either you compare that to a chart or you have a meter that reads that color change and gives you a value. Titrometric, which is basically adding a reagent to a sample until it changes color, it produces an end color, and then you basically count up how many drops or how much of this reagent that you've added, and that gives you a calculation and results in a reading for the value of whatever it was you were testing for at the end. And electronic, usually these are colorimetric, but they can be probe, ISE, ion selective electrode type of instrumentation. But usually this either involves a colorimetric or just using the probe, and it'll give you a digital reading. These are usually the easiest, and they're becoming a lot more common. Colorimetric methods, again, I went over that just a little bit, but it usually involves adding some sort of reagent. I'm not going to just read this for you, but it's a measurement of a color change, basically, whether you're doing it by eye or whether you're doing it by meter. That's all it is. You're measuring a color change. Titration, same type of thing. You're titrating till you get to an end color. Then you're counting up drops or you're counting up titrant used, and you're doing a conversion or a calculation, and you're getting an end product. I don't know if anybody has enough time to read all that before moving on to the next one, but again, this will be available later if you need to look over it. Here are some of the different types of colorimetrics that are typically used. A test strip is something that you dip into the sample, and then there's either a pad on the end, or if it's a paper, the whole paper itself will change color, and you compare that to a color chart, and you see a typical color chart over there, and you basically compare and find the color. And then that color correlates to a certain number of whatever it is you're trying to determine, and then you would record that. The next step up from that is all the way at the bottom on the right, which is like a slide comparator. That's our version of one, where you would put it in a test tube and get a color change and slide that bar up and down until you match the color and then read the outcome. And then, of course, a colorimeter, digital colorimeter, where you're basically letting that sample turn color, and then you're putting it in the meter and hitting a read button, and it's simply giving you a digital readout. That's the easiest by far. Different types of titrometrics, so the direct reading titrator, which again will be a volume type where you're adding a reagent till you get a color change, and then if you look on that little syringe there on the left, there are increment levels on there, so you'll see how much you used, and that'll help you determine how much of any particular constituent you have. The middle one is a dropper bottle. That's a drop count type test where you're going to be adding reagents to the sample drop by drop until you get a certain color. Then you're going to count how many drops you added, and that'll help you reach your end number. Automated burette, that's usually done in a laboratory, but it's the same type of thing as a direct reading titrator in a way, in that it has increments on that. You see that long tube that sticks out the top. It has increments in it, and then that container on the bottom simply will have the reagent in it. And you'll open up that little valve and let it go drop by drop until you get an end color, and then you'll read the increments on the side. Usually you'll see those in a laboratory. If you have a wastewater facility or something like that, sometimes they'll have those at individual stations, but you're not usually lugging those around in a vehicle with you. Electronics, a few different kinds. Spectrophotometer. The picture of the meter we're showing right there is actually a turbidity meter. Turbidity meters are a little different than colorimeters, even though sometimes they'll look very similar. They're simply for measuring the turbidity or the haze of the water. Handheld meters, which are becoming a lot more common. These are the ISE ones I had mentioned before, the ion selective electrode type meters. They started out just doing pH, but you can do a lot more with them now. Dissolved oxygen, there's even ones for fluoride, so they're becoming a lot more common. And then a colorimeter, this one we're showing here, the Color Q, is a small handheld one. It basically is great for field use, and these are becoming a lot more common too, easy to use. Calibrating and maintenance, the best way to go about doing this is always follow the guidelines of the manufacturer. Every manufacturer, when you receive a meter or you receive a kit, or even if you receive test strips on the side of the bottle, there'll be some guidelines on how best to use this equipment and what temperatures to store this equipment in. Differences in temperature, differences in humidity, that type of thing can make a difference sometimes on meters and on reagents. Basically, you want to make sure that you're following those guidelines all the time, and you're checking to make sure that everything is the way it's supposed to be. Before you do any testing, when you have that sample cell that you're actually going to be adding the reagent to, it's never a bad idea to rinse that thing 3 times or more if you've got access to enough sample. If you have a limited sample, at least 3 times. You don't want to have any residual reagent from a previous test or any contamination inside there if you can avoid it. Storing them properly, again, sometimes light can affect it, indirect or direct lighting. Temperature certainly affects it, so leaving them out in the vehicle and it's going to freeze overnight and the reagents freeze up and then thaw, that could be a real problem. So you want to be conscious of how they're supposed to be stored. Making sure the reagents have not expired. This seems like a real simple thing, but it's probably one of the most common concerns that we get through our tech services line. People get strange readings when they use a kit or use a meter, and we have them check the actual date that it was made to see if it's an expired reagent, and a lot of times it'll end up being an expired reagent. So the first thing I would check is if you get odd readings or things aren't working the way you're supposed to, is I check to see if that reagent is still inside its useful date, and that may eliminate some of the problem right there. And again, cleaning and storing, especially with electronic meters, you really want to follow the guidelines that every specific manufacturer states for cleaning their meters. Not every solution that you can use to clean a meter will work on every meter. Some can actually cause damage to the chamber that you're putting the sample in, or maybe even light sources or the outside of the meter. So even though it seems a pretty straightforward thing on how to clean something, check your manufacturers. Almost every manufacturer puts a little thing in their book that comes along with it, their instruction manual that will tell you how best to clean it, what solutions to use, and how to store it. The things you're most commonly going to be testing for in a field type situation are chlorine, if you're on a system that adds chlorine, pH, which is just a basic test for how acid or alkaline, how acid or base the water is. Temperature. Temperature tells you a lot about where the water is as far as where it's progressing through the system. If it's been sitting in the line for a long time, the temperature will start to go up. If it's water that's constantly moving through the system, the temperature will be down. So that can give you a lot of data as far as how accurate your sample is going to be for what's representative for your system. Iron, that's a big one for especially if old pipelines, a lot of the old existing infrastructure out there that had the old cast iron lines in the ground, and sometimes in homes and things of that nature too. Certainly in wells you'll get iron, but iron testing is done quite a bit when you're flushing out systems, when you get discolored water concerns. Iron is a secondary standard, but most governing bodies will treat it as a primary, which basically means it's not a health problem, but because it causes discolored water, they want you to treat it like it could cause a health problem and get out there and deal with it as quickly as you can. So usually if you start getting dirty water complaints from customers, you have to get out there and flush the lines as quickly as possible. And obviously you're going to be wanting to test the iron while you're doing that. You're not going to want to run samples back continuously to a laboratory. And it's pretty easy to do iron testing in the field. Fluoride, if you're working on a fluoridated system, not all systems are fluoridated. It's basically up to the supplier if they want to start fluoridating or not. Once you start fluoridating, though, you have to continue to fluoridate from then on, and you constantly need to be checking to make sure you're not adding too much or too little. So fluoride tests didn't used to be done in the field too much because they were kind of a cumbersome test to do, but new technologies have come along and made it a lot easier, so fluoride is tested more now. Turbidity, this will tell you the haze or how turbid your water is. It has a lot to do with microactivity is more common in very turbid water, so the EPA wants turbidity checked on a regular basis, and now that can be done fairly simply in the field. And then dissolved oxygen conductivity, those types of things, mostly in wastewater, but they're still done in the field. You want to make sure that your sample site is easy to get to. It's clean, direct. If you can adjust the flow so that you can make it run hard when you need to flush it out, but then dial it back when you go to collect your sample, that's certainly the best way to do it. The location, making sure it's representative of what it is you're testing for, what it is you're trying to find out. And then it would be easily accessible. If you have to go back to it on multiple occasions, if you're doing a study, sometimes EPA or whoever is conducting the study will want multiple samples from similar or the same locations, so you may have to go back time and time again to the same locations. So you don't want it to be a location that's extremely difficult to get to if you can avoid it. When you get to that location, and this is mostly for when you're doing sampling at the taps like inside homes, but most of these things can apply to whether or not you're doing it at a well site or in a pumping station. But especially if you're in somebody's home, you want to turn the tap on and let it run. Reason being that most of the time when you're testing inside of a home especially, it's a lot of plumbing and that water's just sitting in that plumbing. So if you just turn it on and collect a sample right away, you're not really getting a representative sample of the water that's being supplied to that home. You're getting a representative sample of the water that's sitting in their plumbing. So if you run it for 3+ minutes, usually you've cleared out all that plumbing and you're starting to get water from the street, and provided that they're not sitting a half a mile back from the street. Then you want to collect that sample in a container. It's usually easier to collect it in a larger container and then use that container to pour off into sample cells. It just makes it easier to control, and then you can collect a lot more sample that way so that you can, like I said, rinse it out 3 times, or if you have to do multiple tests. Once you've collected that, most of those tests you want to do as quickly as possible. Things like pH, chlorine, they're going to change a bit over time. So the quicker that you can perform those tests, the more accurate your readings are going to be. If you're testing for chlorine, you want to make sure that the tap that you're using, especially if you're in a treatment facility, is far enough away from where you're injecting that chlorine to be representative. If you have the tap that's directly after where that chlorine pump is adding the chlorine while it's on and actually physically adding chlorine to that water supply, you're going to get really high readings. Whereas if you allow it to blend out a little more, you may get a more representative reading. So usually you have to move off a bit from where it's actually being injected. And the other side of that is if you accidentally have the sample tap this before the chlorine injection, you're never going to get chlorine. So just be conscious of where the chlorine is being injected into the water. Again, easy access is important, especially if you've got to go back to these places time and time again. It's easier to get to, the easier it makes it for everybody. Always run the water for a few minutes if possible. It's just always best to get a good representative sample that way. And you probably want to collect in that container that you're collecting the original sample and enough to do a few tests. If you just collect a little bit of sample and you say go back out to your vehicle or wherever to do your tests, and then you run one test and you're out of water and you have to go back and get more, that's inconvenient. So try to take enough that you can at least do several tests and a little more. It's always better to have more than not enough. With chlorine testing, this is pretty common for every type of test kit or meter out there. It follows the same sort of procedure. This is basically our procedure here at LaMotte for doing it, but most of them you'll find will be fairly similar to this, if not right on the money. You're going to fill up whatever that container is to the marked line. Usually it'll have a line or an indication of how much sample to use. It's important to make sure that you're using that line because usually it's, you know, a designation of 10 ml or 25 ml, whatever. But that reagent you're going to be added is calibrated to interact with that volume of water. If you add more water than you're supposed to, your reading is not going to be accurate. In the same way, if you're not adding, if you don't have enough water. So be very aware of how much water is required to do the test because it matters related to the reagent. You're going to add the reagent. In this case, it's our chlorine DPD tablet. But whatever the reagent is you're going to add, you'll see it change color, especially with chlorine, pretty quickly. And you're going to put it into the meter. You're going to compare it to a color chart as quickly as possible and record that down as parts per million. Some people still use milligrams per liter, but parts per million is pretty much the accepted standard. The difference between parts per million and milligrams per liter is there is no difference. They're exactly the same. They are like values, so you can use either one. Parts per million is pretty standard. And then if you're going to do, this was basically for a total test, if you're going to do the free first and the total, which would be the next one, you want to save that because to the free, the one that's already reacted with the free reagent, you're going to add another reagent to get the total test. So, and that would be here. You're adding the number 3 tablet for us. And do the same thing. You insert it or match it to a color chart, hit a button, and then that'll basically give you your total. Once you have your total and you're free, you can perform a calculation to get your combined chlorine. The only difference between total and free chlorine is total chlorine is all the chlorine that's available in a certain sample, whether it's already hooked up to an iron molecule or whether or not it's already managed to kill a pathogenic bacteria. The free chlorine is just chlorine. It's just wandering around waiting for something to hit it that it can attach to. Free chlorine is important because that means there's chlorine available to kill anything pathogenic that might come into that water. That's what most governing agencies want to see is how much free chlorine is still there because they know if you have enough free chlorine, the water won't be contaminated with pathogenic bacteria. And then you're going to really want to rinse those tubes out after you're done to make sure that you're not leaving any residual reagent on there. pH is usually an electrode type of test. It's certainly best done in the field. You just put the electrode into the sample, you move it around, agitate it a little bit. You'll see that the display will move, the pH will move a little bit, but eventually it'll sort of settle out and decide on a number. Once you get that number that it's decided on, record that number. That's your pH. And then turn it off and rinse the electrode at the end so we're good to get all those contaminants off of it and replace it and replace the cap that comes along with it, whatever the manufacturer's cap is. You want to keep that cap on there between uses so you don't bang that electrode and break it or you're not exposing it to the elements any more than you have to. So replace that cap between each use if possible. If you're doing a colorimetric type pH test, there are a few out there. It's kind of the same as all the other colorimetric type tests where you fill the test tube, you add the reagent, and then you put it into the reader and hit a button, or you're comparing it to a color chart, and then you record that as your pH. The test strips, they're used quite a bit in pool industry, but they're also used as quick checks with wells, things of that nature. You're just going to immerse that strip in the sample for whatever the specified time is. Now that's usually pretty quickly, but and then you're going to remove it and compare it to the chart. You don't want to wait too long. Usually once you're done exposing it to the sample, you want to read it right away because it will change color over time. Iron follows the same principles as any of the other colorimetric tests in that you're simply filling up a test tube, adding the reagent, putting it in the viewer or matching it to a color chart, and then recording your readings as parts per million. And with the test strips, it's the same procedure. You just follow whatever it says on the side of the container that you're getting the test strips out of. So the times will vary depending on what you're testing between iron and chlorine. Sometimes there may be some different time levels that needs to be exposed to it. So make sure that you're doing that the proper way. And again, compare it to the color chart as quickly as you can. Fluoride with an ISE, the ion selective electrode with that method is that it's sort of similar to the pH one. All you're doing is turning this meter on and you're immersing it in the sample. Wait until the display evens out, and once it arrives at a number, you have your fluoride in parts per million. You record that and then turn that meter off, rinse that electrode off real good, and again, replace that cap. It's always better to keep that cap on as much as possible. Colorimetric fluoride, this is usually done with a reagent system. And it follows the same principles as the other colorimetric tests, whereas you take your sample and fill a test tube, add the reagent to it, and mix it. You want to insert the tube into the viewer or the meter or match it to the color chart as quickly as possible, as with all the other tests. Turbidity. It's really important that you calibrate that turbidity meter following the manufacturer's instructions. Usually they'll come with standards, and it's important that it be calibrated properly, usually on at least a daily basis, if not more. So follow the manufacturer specifications for that, but make sure it's calibrated properly before you use it. And then you're going to fill your test tube to the line. Put the sample into the meter and press the read button, and you get a reading. Now this time when you get a reading, it will not be in ppm or parts per million because those are not units that you can use to measure turbidity. It will come out in NTUs, which is nephelometric turbidity units. That is the standard for measuring turbidity now. There are a few other different kinds of units out there, but most everything wants you to do it in NTUs. So then you simply record that reading in NTUs. Dissolved oxygen, conductivity, temperature, these are usually done on the ion selective. Most of your pH meters, dissolved oxygen meters, conductivity meters, they all have a temperature readout on it. If you need to carry a thermometer along with you too, that's fine. I used to carry a thermometer all the time, but you can use that temperature readout right on the screen of these meters to get your temperature reading. So when you're doing your pH or you're doing your dissolved oxygen, just take that temperature reading right off of the screen, and that'll work as your temperature reading for that sample. And then even with the dissolved oxygen conductivity, it's the same as the pH. You're simply immersing that electrode in the sample, letting the reading level out, and then recording it, pressing it off, pressing the on-off button. Make sure you turn the meter off so you're saving on batteries, and rinse it off and cap it. One thing I do want to point out, going back to the sampling, is that when you fill up a sample tube and you add a reagent, when you go to mix that reagent in there, usually those samples come with a cap, the sample cells. Use the cap. Don't put your finger over the end of it and shake it that way because your finger will affect the end reading. There's a reason why they put a cap in there, and there's a reason why we put a cap in there, because it will affect if it comes into contact with your skin. There's oils and things on your skin, no matter how clean you are. And it will make a difference as far as that end number is. So if there's a cap with that, use it. If there's not, get one that has a cap. Recording the results, use the proper label. You don't want to get out there, take a sample, do all your tests, put the label on the side of the bottle, write a bunch of stuff on it, put it into whatever container you're using to transport it, get it back to your central location, pull it out, and realize that the sample or the labels were not the proper labels, and the condensation has completely destroyed them, and all your information is lost. So, and that's important with the proper pen too. Don't use something that's water soluble. They make labels out there specifically for this type of application to put on the side of sample bottles that are going to have condensation and get wet, so that they don't fall to pieces, and they have pens out there that aren't water soluble. Take the time to make sure you have those before you go out, because it's nothing worse than coming back from a whole day of sampling and realize that every sample you took you have no information on because you used the wrong kind of label. The kind of things you're going to be putting on that label when you do your testing is you're probably going to want to put on there where you actually took the sample, so that you'll know where that sample is located in case there's more tests that have to be done on it. What time you took the sample. That matters depending on what's going on in the water system. Different times of the day, you get different results. What things you tested for and what their values were. If you're testing for the pH, you're testing for the chlorine, you tested for the iron, make sure all that information is listed on the label. You probably also want to put your name somewhere on there so they'll know who it was that collected the sample in case a week later they have some questions on what was going on in the area at the time, if they get any special readings. All these things should be recorded on the label, and if you're carrying a log book or something with you too, you want to make sure you have all that information on there too. Also, any special notes, anything that might pertain to or make the people back at the central location you're taking these samples back to for further analysis. We'll fill them in a little more on why exactly you collected the sample, or why maybe the readings are a little different than what they expect, if it's part of a flushing program, if it's part of a lead and copper program, if you went to take that sample but you noticed that there had been a fire up the street earlier in the day, and maybe that's why there's higher iron levels now because there had been a huge rush of water. All these things matter. They paint a better picture of what exactly was going on out in the system when the sample was collected. Again, more information is better than no information. Some of the things that you're going to have tested for back in the laboratory, these are things that usually aren't done in the field. Volatile organic compounds, these are things that you have to, there's no way to analyze them in the field right now. They require those big machines that commercial laboratories have, mass specs and things of that nature. You may be collecting these samples. You're probably not testing for them. Volatile organic compounds, mostly when you test for those, it's a sample tube and it has a gasket in the top, because you can't have air left in that sample because these compounds are volatile. So if you have a little airspace in there while you're transporting this sample, all those volatiles are going to basically go up into that airspace, and then when you open that sample up to go to analyze it, it's going to escape, and you're always going to get zero volatiles no matter what's actually in the water. A side note on that too, when I very first started taking samples, I was going out to a sample site that had an outside sample tap, and it was winter. And I'd pull my vehicle up, get out, take the volatile samples, go about the rest of my day and take them back to the commercial laboratory, and all of a sudden this one well started having the volatile skyrocketed. So I went back out and resampled, which is standard procedure, and got back, and a few days later they came back and they skyrocketed again. So we had to figure out what was going on at this site. So drove out again and had somebody else go with me, and we were looking things over, and we noticed that when I pulled up, because it was winter and I wanted to get as close to the sample tap as possible because it was cold, I actually pulled the exhaust right next to where the sample was being taken. So as I was collecting that sample, I was also collecting my exhaust, which is full of volatile organic compounds. So there was nothing wrong with the water coming out of that site. It was bad sample procedure. I had pulled up, not thinking, pulled up my car right next to it, and so I was collecting the fumes from my exhaust. And that was skewing that reading. That's just a lesson in being aware of your surroundings. When you collect a sample, things can affect it. In that case, my exhaust affected it. Bacteria, same type of thing. Usually, if you're working with a commercial laboratory or if you have a micro laboratory, they'll provide you with the vessels, the sample vessels that they have to be collected in, the bacteria has to be collected in. You got to be real careful with them not to touch the inside of the bottle while collecting it, or touch the inside of the cap. You usually have to run the water for a bit before you can collect that. Reason being is even though you might not have pathogenic bacteria on your fingers, if you have any bacteria at all, which is possible, it may make the sample invalid or have too numerous to count. It'll just make it so that there's so much going on in that sample that they can't tell if there's any pathogenic bacteria. So yeah, using proper sample procedure with bacteria is probably one of the most, has the most prerequisites for how you collect the sample, how you store the sample, the temperatures it has to be kept at, how it's transported. Follow all of those because it's important that you're getting very accurate bacteria readings from out in the field as the water people are drinking. So I would consider that pretty important. Total trihalomethanes, these are disinfection byproducts. This is something that really came to light. I mean, we knew about it before, but in the 90s is when most of the testing, the EPA started wanting to do field studies. The place I was working took place in some of these field studies, finding out that when you add chlorine to water, as it's sitting in the system over time, chlorine is pretty aggressive. That's why it makes a great disinfectant. And it'll start adhering to other things, bromines, other things in the system, and some of these eventually could create cancer-causing compounds. So they wanted to take a look at what was going on out in these systems and what kind of cancer-causing compounds these were resulting in. And they found out it was quite a bit. So you still have to test for total trihalomethanes. Usually they want you to test at the extreme ends of the system, so it might require some homework to sort of look how your water's flowing, because even if you drive all the way out to the furthest development you know about and go all the way to the very back of that development, doesn't necessarily mean that's the end of the system. I mean, it could loop around and come back up, and the entrance to that development could actually be the end. So you want to take a good look at how your water's flowing and get an idea of where the extremes of that system is before you collect your sample. Lead and copper. Lead and copper survey is a big thing for drinking water. Has to be done on systems on a yearly basis, sometimes more. Corrosivity plays a big part in that. What they're basically looking for is how much the water is causing pipes and old lead plumbing to leach lead and copper into the water. Usually these samples have to be collected by a homeowner, so you have to leave a bottle with them, and the water has to sit in those lines without being used for about 6 hours or so. Then when they first turn on that water, that first burst of water that comes out needs to be the one collected. This is one of those situations where running the water for 3+ minutes is not what you need to do. This is actually one where that first bit of water that comes out is what we're actually interested in finding out, because you want to see how much lead or copper actually leaches into that water as it's sitting in the pipes. Phosphates, lead and copper deals with corrosivity. In some situations, what the systems will use in order to control iron and things that are leaching in there from corrosive water over time is like a zinc polyphosphate. They add it to the water in order to coat the mains, and it prevents these things, iron, things like that, from leaching into the systems. If you're adding zinc polyphosphate, you have to be out in the system checking. It's a regulation that you check and keep an eye on that because it can't be too high, but it's also just good business, because if you're feeding way too much phosphate, you're going to be using a lot more, and it's going to cost you a lot more money. You may not necessarily have to feed at those rates, so you're going to want to monitor and see how much you're actually feeding. Inorganic compounds, arsenic, mercury, these types of things are compounds that have to be done on some pretty advanced equipment, and so basically you can't do that test out in the field. You can collect samples for it, and again, there may be very specific ways you have to collect those samples, so you're going to want to follow good procedure, but you can't really do those tests in the field. There are some arsenic tests that can be done in the field. They're usually quick check type tests, but that's still one that's very common to be done in a commercial laboratory. And I guess that basically brings me to the end of the presentation as far as what I need to say, so it's down to question and answer.
Okay, Ernie, thanks a lot. I'm afraid we've kind of, our allotted time has expired. I don't see any questions currently in the queue, so we'll follow up with an email to those individuals whose questions appear after the session has ended. Just a reminder, this webinar is going to be posted on YouTube over the coming days. and will also be available on the LaMotte Company website. The next webinar in the Rural Water webinar series will be announced in the near future. Thanks for joining us, and have a great day.